All right, I'm Bielkwickz, and I'm the group number 1. I'm group reporter for the experiment number 3 refrigeration cycle. So the introduction, we're going to be looking at the vapor compression cycle for a refrigeration and heat pump, which are two opposite systems. We're going to analyze the performance of them, and the objective is thermodynamic analysis of a heat pump. We're going to measure the coefficients of performance and describe it in a pH diagram. And the COP, which is, the efficiency would be greater than 100%, but the COP is going to be more, no, I'm sorry. The efficiency is less than 100%, whereas the COP is going to be greater than that. So, in general, a heat pump is going to absorb heat from a low temperature and reject it to a high temperature source. It heats a space in cold weather and cools a space in warm weather. So a good example of the heat pump is, anything whenever you have hot air, you want to cool it down, and the opposite is a refrigeration cycle. So in the summer, it'll cool a room. In the winter, it heats a room. So the 4 components of a refrigeration cycle is compression, condension, condensation. Is that right? Condensation, expansion, and evaporation. All right, so theory. COP is the ratio of the magnitude of the desired commodity to the magnitude of the expenditure. The expenditure is the power consumed at the compressor. The desired output is either refrigeration or heating. And the pressure and temperature transducers, which measure the pressure and temperature at various points during the cycle, are used to find the enthalpies in the pH diagram and the COPs. So it depends on where you take that number, the COP that comes out. So one part of the experiment is the thermostatic expansion valve. And this is a simplified example. It's a valve that controls the fluid flow. It used in refrigeration or heat pump system. It regulates the flow and pressure, which is important because we're trying to find the data based on a certain flow and pressure we're inputting into the system in liters. So now going on to explain the pH diagram. So from 1 to 2 is compression, so the first part of the cycle in a superheated state. So what you're going to have is that work and heat is going to be put in and compressed, and then it's going to have a straight line 2 to 3 condensation, and that's where the pressure stays constant, but the enthalpy decreases, so it's losing heat to the system, to the outside. And then 3 to 4 is expansion, so enthalpy stays the same and pressure decreases. And then from 4 to 1 back is the evaporation. When it returns to state number 1, heat is put into the system, and then it'll start the cycle again after that. Experimental values. So as stated before, you have the compressor, condenser, and all those things. And the power consumed by the compressor was 0.4029 kilowatts. The temperature at the inlet of the condenser, 21.9. Temperature at the outlet, 26.2. And the inlet flow, original parameter values is 5 liters per minute. Experimental data shown. So at the inlet of the compressor, and there's a diagram of this, but it's a little complicated, so I just put the data here. The temperature at the inlet of the compressor stays constant. As you can see, 2.8, 2.8, 2.8, and 3 liters per minute, 4.5 liters per minute, and 6 liters per minute were tested, so it stayed the same. Cooling pressure at the outlet of the condenser more or less stayed the same, slightly increased. If we would have gone to like 15, 20, 30 liters per minute, it would have probably increased more. And that's another thing for the experiment. We could have done, instead of 3, 4.5, and 6, you could have done 3, 10, and 20. You could definitely see more of a trend looking at those numbers. Cooling temperature at the inlet of the compressor stays pretty constant as well, slightly increase. Outlet of the compressor slightly increases. Outlet of the condenser slightly increases, and outlet of the expansion valve slightly increases. So as you can see, as the flow rate in liters per minute is increased, usually the temperature, pressure, and all these numbers increase with it. So my data that I did, you had to find the electric power, produced heat, and COP. So I found the heat from MCV delta T. I plugged in the known values and found that produced heat would be about, the electric power would be about 71.896. And then COP, I found to be about 446, which I understand is extremely high and not realistic. But going on the calculations, I'm not going to try to skew the data. So that's what I found based upon the Q and W calculated. And then pH diagram showed the same thing I explained. Predicted value 80%, my value 446, obviously too high, but the COP would be greater than 1 because the flow rate over the work is the formula for it, and the flow rate would be higher than the work. Possible uncertainty, not giving the time, the system enough time to become stable, not using the correct flow rate for the given experiment, temperature changes for long time periods, or human interference, like messing with a certain thing or not clicking the right button, something like that. References, thank you. Any questions?